Hello students, in this video we're going to be looking at graphing absolute value functions, specifically linear absolute value functions. So we're going to look at a few different approaches, but before we do, let's just conceptually make sure we understand what's going on. So to the left here, I just have a normal linear function here. We've got y equals 2x plus 5. Well, y equals 2x plus 5, nice and easy thing to graph because I know my y-intercept is 5, and I know that my slope is 2 over 1. So if I were to go up 2 over 1, I would end up with another point on the line. So what does an absolute value function do to the graph that we have before us? And that's sort of what we have going on over here. We have y is equal to the absolute value of 2x plus 5. And if you want to pause the video and think about that and kind of imagine what's going on, by all means, feel free to do so. I'm just going to dive in with my explanation right now. So what this means here, this 2x plus 5 all absolute value means that my y will always output to a positive in this case right here, because the whole expression on this side, on the right side, is it's being absolute valued, if we want to say it like that. So when I look at my original function, I have to think about, okay, my y values of 12, of 10, of 8, those are all fine. But all this down here, all these negative y values, well, because they're being absolute valued, they're all going to reflect up. So I normally have a y-intercept, or I still have my y, or an x-intercept, excuse me, of negative 2.5, and my my y-intercept is still 5. So this part of my function stays the same, but all this part down here ends up being reflected back up. So for instance, if I can find, none of these points are very nice looking, but what I can do is I can sort of reverse engineer what's going on here. So this, on this side, my slope is plus 2 over 1. I know that's not to scale there, and I apologize for that, but I'm going to just look at this side and do the same thing. So here I go up 2 and over 1 this way, and I'm going to have, and this is not going to be drawn very well, my apologies, but essentially what it is, it's the other side reflected up. So here I have a slope of a negative 2, and here I have a slope of 2. And the reason this side's negative 2 is because all this can't exist because all my y values are negative and they get reflected above the x-axis. And that's what happens when we just absolute value everything. So when we're talking about absolute value linear functions, these are, and you're asked to find the features, these are all the features that you're gonna have to find. So if we ask for the slope, well, there's always gonna be two slopes. There's gonna be the slope on the left side of the vertex and the slope of the right side of the vertex. And by the way, that right there we call the vertex. You're going to be asked to find x-intercepts if they exist. So sometimes we're going to have cases where they don't exist. You're going to be asked for a y-intercept, which always exists. You're, of course, going to be asked for the vertex, the domain and range. And so like a parabola, the range is restricted by the vertex, and the axis of symmetry. So if we keep our vertex, if we write our absolute value linear functions in vertex form, it makes graphing them nice and easy. So much like with quadratics, we've got a vertex form for quadratics. You'll notice this looks very similar. We've got a vertex form for absolute value linear functions. Now, of course, you can get stuff presented in different forms, but to start us off, this is what things are going to look like for us. So here I have the absolute value of 3x minus 5, absolute value plus 1. So right off the bat, I know my vertex is going to be 5, comma 1. Just like when we did quadratics, this sign right here gets flipped, and because you want to think about what the horizontal translation is, and by the way, just a quick revision, this is like our horizontal translation, this is our vertical translation, and that right there is our vertical stretch. So our vertex is 5, 1. X and y intercepts I can't just tell by looking at, so I'm going to skip over them for a second. My domain, x is real, just because if we're unsure of that, I can just go and think back to what this did here. I can put in any x value I want and not get an error, and that's why it continues on forever to the left and on forever to the right. Same thing here, like no matter what number I try to imagine putting in there, it's always going to give me, I'm always going to be able to evaluate the function. My range is going to be restricted by my vertex. And so I can tell that because I've got a positive, because my vertical stretch is positive, it's going to look like this. So I know my range is going to be y is greater than or equal to 1. Y is real. Of course, you can write that in a more formal way if you'd like. My axis of symmetry is always my vertex. X is equal to 5. Always my vertex, I should say, with a linear absolute value question. Direction of opening is just upwards or positive. And my slopes are plus or minus 3. So let's actually graph this bad boy out here. So I'm going to go -5, sorry, 5 and 1. So 5 and 1 puts me right here. And I'm going to go up 3. Oh, so I have to be careful here. So I'm going to go up 3 over 1 and up 3 over 1. And you can keep that relation. You can go up 3 over 1 from this point. So if I wanted to go up 3 over 1 and then up 3 over 1, you can also just always orient back to your vertex and go like up 12 over 4 if you want. As long as you maintain that relationship is fine. And so I'm going to try to connect these with as straight as line as I can muster, because we have slopes, we got straight, these are linear functions. So right away I can tell that there are no x-intercepts, there's none. And I'm going to show you how we can prove that in a second. My y-intercept, it always exists, and I can see that my line is going, it's going to hit the y-axis somewhere around here. Let's figure out when that is. So if I want to find my y-intercept, I know right away that my value of x is 0. So I'm going to come down here and I'm just going to say y is equal to 3 onto 0 minus 5, absolute value, plus 1. And then I'm just going to keep evaluating. So y is equal to 3 onto -5 plus 1, and that -5 is absolute value. So 3 times the absolute value of 5 is going to be 15 plus 1, and that's equal to 16. So my y-intercept is 0, 16. And did I do a pretty good job there? I did an okay job. It should be hitting right there. Not the steadiest of hands. But oh yes, before I move on, I just wanted to address, let's say you didn't graph it or didn't realize that there was going to be no x-intercepts. Let's try finding an x-intercept just for fun. So let's say I know that when I have a y-intercept, my function is equal to 0, my y is equal to 0. So 0 is equal to 3 onto x minus 5 absolute value plus 1. Minus 1 to both sides, so I've got -1 is equal to 3 onto x minus 5. Then I'll divide by 3, and so I've got -1/3 is equal to the absolute value of x minus 5. This right here, not possible or impossible, because the absolute value can't evaluate to a negative. So at this point right here, that should be the other trigger to say, okay, it doesn't work, I can move on to the next feature. And if you're asked to prove it, this is a valid way to prove it, along with graphing it. Like if you graph something and blatantly show that, hey, there's clearly no x-intercepts, that's acceptable to say as well. Let's do another one before I end this video here. So again, try pausing the video if you'd like to do it yourself, but otherwise I'm going to dive right in. So excuse me, I can see here that my horizontal stretch, my horizontal translation and vertical translation are -1 and -7 respectively. Going to skip my intercepts. Domain, x is real. My range, I'm going to be opening downwards, so my function is going to look like that. So I'm going to have y is less than or equal to -7. Y is real. Axis of symmetry, x is equal to -1. Direction of opening is going to be downwards because of this negative in front of the vertical stretch. And the slopes are going to be ±4. So let's graph this out. So I'm going to have a -1, -7 puts me into here. And then I'm going to go down 4 over 1. So down 4 over 1 puts me there. Down 4 over 1 puts me there. And of course I can continue that, but with straight lines, you just need 2 points to connect them. So something like that and something like that. Now, just by happen chance, I actually just found what my y-intercept was right there by just going down 4 over 1 from there. So it looks like it's going to be happening at -11. I can verify that. Again, clearly I'm not going to have x-intercepts, so none. And it looks like my y-intercept is 0, -11. And again, you can verify that by just making x 0 and saying, okay, -4 times 1, -4 minus another 7, yeah, -11. And that was just by happen chance that happened there. Yes, so I'm going to make another video specifically about piecewise functions. We'll talk about that in the next video. However, if you're looking for help with this stuff, please come find me in class. And if not, I'll see you in the next video.